Okay, so last time, I think it was the week before the midterm exam, we started talking about part of speech tagging, and let's make a very quick overview, review. Okay, we said that for any natural language, we have parts of speech. That's the function of a word within a sentence. We can say that the nouns and verbs and adjective prepositions, adverbs, these are usually all available for almost all the languages, and we have them in Turkish or in English. İsim, fiil, sıfat, preposition is edat. Is it edat? Zarf. We don't have articles. Interjection is conjunction is bağlaç. Interjection is kind of bağlaç, zamir, etc. So, I think most of the Turkish terms are Persian, right? Zarf, zamir, Farsça değil mi bunlar hep? Zarf, zamir. Because they sound like Persian. Okay, so that means what? That means that they are available in Persian too, in Arabic too, the Turkish too. Although these are very, very different languages. What is Persian? Is Persian close to Arabic?
No.
What? What is Persian? What?
In the European language.
European, really?
Indo-European.
So it is Arabic?
No.
Well, Arabic is like in...
Semitic language.
Is it Semitic, really?
Yeah.
Oh, okay. Whatever language you look at it, okay, if it's a natural language, then you usually have some of them, and in some languages we don't have these like articles, right? But they are not as prominent as the other languages, etc. So our task is, given a word within a sentence in a given context, okay, we need to mark it with one of these labels. So it's a classification problem, but I mean, by looking at the verb itself, this dictionary meaning, we cannot mark it as noun or verb. We have to look at this function within the sentence. That's the part of speech tagging, and these are some examples, and I'm going to skip those. Why is it important? It's important because without knowing a word's part of speech tag, you can't do machine translation, right? You can't do machine translation. I mean, sometimes it is important to know the function of that word so that we can pronounce it right, okay? So it's a very well known and a very well known problem. It's a classical problem, and we are going to look at it. And I think we looked at, okay, I'm going to skip this one, I'm going to skip those, and okay. Pantry bank is a very large corpus. In this corpus, I think it is from 1990s, okay. They marked all the words with one of these tags. There are 45 tags, much larger than 8, right? But I mean, in English, so this is, you don't say it's just a verb. It says either the verb base form, past tense, ing form, right? Past participle, or the verb non-third singular present tense, etc. Verb third singular present tense, and etc. See, 1, 2, 3, 4, 5, 6, 7, whatever. 6, 7 different verb tags, just for the same thing for the adjectives, the same thing for the nouns or the adverbs, etc. If we do the same thing with what? With other, okay, brown tag, okay, brown corpus, they had 87 tags, okay. So the number of tags and the definition of tags changes from corpus to corpus, changes from expert to expert. That's why we cannot say that, okay, I mean, given 1 million word text, we cannot say that this is the tags of this text and I'm 100% sure about it. No, even the top human performers, PhDs in linguistics, they cannot agree on some of the tags that are available. And ambiguity is very common, okay? So you say that in this 87 tag original Brown corpus, okay, 44,000 words, unique words, are unambiguously marked with a tag, just a single tag, but 5,500 is going to be tagged more than two or more than two. Okay, so that means what? It's like 10% of all the words are ambiguous. Some of them are very, very ambiguous. Okay, because I mean this one, still and down, can be tagged with 7 different tags for this corpus. So there is ambiguity. Then if there is ambiguity, it's an artificial intelligence problem, and we need to solve it. The first method to solve these tagging problems is this one, rule-based tagging. Okay, and we looked at it. And what was the nice thing about rule-based tagging? It seems very logical. You say that I know the rules of tagging. Okay, if this happens and this happens and this happens, then okay. For example, if you see I have, okay, and if there is a verb in there, okay, whatever the verb, it has to be marked with VBN, right? That's your rule. But that doesn't work all the time, okay? That doesn't work all the time. I have eaten, okay? What if eaten is a name or a disease, right? So it may not work. So I mean, by writing these kind of rules, it seems logical. It looks like it's going to solve everything. No, it works for the 90% of the cases. For the rest, 10%, it doesn't work very well. You have to add more complicated rules in your rule set, and then your rule starts contracting. Your rules come in contradiction with each other, and that's not going to be good. So that's why we say that the rule-based tagging only works for very small data sets. For the large ones, we are going to use a stochastic approach, hidden Markov model. Okay, hidden Markov model. Hidden Markov model is going to use the probability theory again. And let's look at them. I think we looked at the thing. Where is it? Yeah. This is what we are going to say, okay? I have the language model that we learned in the previous chapter. Remember the language model, statistical language model, okay? Given these words from 1 to n, what is the probability that I assign these tags to these words? So given the n words, I am going to assign these n tags. Find me such tags such that this probability is maximum. Okay? This probability is maximum. Okay? So that's what we are going to do. I mean, so if we can find such a formulation, let's formulate this. Let's calculate these kind of probabilities using the data that is available already to us, Brown corpus or the Penn corpus, right? Then we can calculate it, but calculating this is not that easy because for this one, what do we need? We need to calculate. Let's get this probability, right? What are we gonna do? We are going to calculate this count of all these tags assigned to all these words, or count of all these words happening, right? I couldn't do it again. I am trying to write W1N, okay? You need to calculate this, but we have seen in the previous chapter that, okay, given just a 5-word sentence, it is very difficult to find it even in the Google case, right? 5 gram, calculating 5 grams is very difficult. We don't have enough data. So to calculate this value is not feasible because we don't have enough data. Usually you are going to get, I have seen these words together 0 times, and I have these tags assigned 0 times. Okay? So that's going to be a 0 over 0. That's not going to give us anything. You might say, let's use smoothing, but smoothing is going to, when add smoothing is going to give you 1 over 1. That's not going to be good, right? So this will not work. We have to do something else. That's what we did last time. And about how to make it operational, how to compute this value. We are going to invert it like this, using the Bayes rule, Bayesian classification, to transform this equation into a set of other probabilities that are easier to compute. That's what we are going to do. This is what we are going to do, okay? I can write, okay, the original formula like this. Give me the probability of these words happening together. Give me the probability of these tags happening together, and give me, given these tags, what are the possibilities of seeing these words, okay? And since this is an argmax thing, I don't have to calculate the probability of these words because words happened already, okay? So this one and this one is exactly the same thing, okay? This division is not, okay, this division is not same as this, but the chosen tag sequence is the same. So we are going to look at this one, but for that one, last time we did this, remember? If you are going to calculate this, then, okay, then take this assumption from this one, okay, from this one to this one. Say that ignore all the dependencies between the neighboring tags and neighboring words. Only calculate these. Given this tag, what is the probability of this word? Okay, let's do this. Word and tag, let's calculate it. So tell me what I'm going to do. P, TW, WT doesn't matter, okay? WT and PT, right? So what is this? Let me take verb P. I'm not going to fit it in here. P, take verb, P, verb. How do you calculate this P verb?
The number of verbs in the corpus.
The number of verbs in my corpus. But it's not just the number of verbs, probability of the verb, right? So how many times verb happened in my corpus? So if I say, if I have million words in my corpus, okay, I looked at all of the tags of them. Out of those million words, okay, let's say 20,000 of them are, okay, 20,000 of them are verbs. So it is like 2 over 100, right? 2 over 100 is the probability of being a verb. And out of all these verbs, how many of them are take? Okay? Take that one, that's the probability. So calculating this one is not that difficult. I can calculate it. I can estimate it. Okay? So maximum expectation is going to give me this, so I can do this. And for each one I can calculate it and multiply them. I will get this one. For that one, we remember from the Markov assumption from the last chapter, we say that you don't calculate the probability of having this tag sequence in order. We calculate it this way using 2 gram tags because I don't think that I have seen this tag sequence in anywhere. Okay, so I did this and calculating this is not that difficult either. So how this is going to, so it's going to be, so this one, maybe I should write this separately. P given given the article, okay, what is the probability of having a noun after the article? So what is the probability of article nouns happening, and what are the probabilities of articles? Again, it is not that, I forgot about the equal sign there. No. Okay. So it's not difficult either. So I am going to do this multiplication from 1 to n. I know how to calculate this one, and I know how to calculate that one, and that will give me the total probability. So but this one says argmax. So tell me, how would I calculate this? How would I calculate this tag set that makes this maximum? The words are already there. The question is this. Give me the tag set for the I go to school very often. Okay. Just give me some tags for each one, okay? I like you to say, okay, this is my verb, this is my preposition, noun, adverb, very adverb, and often is adverb, right?
Yeah.
Is it adjective, adverb, adverb and adverb?
Yeah.
Very often, yeah, adverb and adverb, yeah, okay. And this one is a pronoun, right? I mean, they gave me this blue sentence, they want the red labels for that one. So what am I gonna do? I will try pronoun for the first one, then verb. I will calculate this probability. Then, but I don't know if this is the perfect probability. Then I will try verb for I and noun for go, etc. For I, there are 45 possibilities. For I, there are 45 possibilities, because if I use the pen tree bank. For go, there are again 45. So it looks like 1, 2, 3, 4, 5, 6. 45 to the power 6 possibilities. I know how to calculate each one, but 45 to the power 6 is a very large number. Okay? Calculate all of them and pick the one that produces the maximum. Merhaba hocam, dersteyim, çıkınca arayayım mı?
Olur abi. Ben de buradaydım. Müsait olursan diyecektim ama çıkıyorum ben. Görüşürüz, tamam.
Telefonun açık mı hocam?
Açık açık her zaman.
Sen beni çok kötü sattın. Ben seni bulacağım.
Tamam o zaman. Saat kaçta bitiyor?
4.30'da. Sen git işine bak, ben seni bulacağım, tamam.
Tamam hadi bay.
Hadi görüşürüz. Bunu kötü yapacağım hocayı. Kim olduğunu görmediniz değil mi? Videoya falan çıkmadı değil mi?
Ama kayda alınmıştır herhalde.
Sesi girmiştir.
Kim olduğunu tanıyamazsınız ki. Eski rektör, tamam mı? Bana bu işi sardırdı, gitti ondan sonra. Okay. Nobody is listening to my lectures anyway, so nobody's going to know it. That's we can't do that. We have to do something different. Remember what we did? I mean, computer scientists, they love this kind of scenario. Okay, they come up with a formulation first, then using the brute first, they try to calculate it, and in the brute first way, it's going to be exponentially expensive, prohibitively expensive, and they're going to say that, okay, we can solve it this way. we are going to do it with the dynamic programming or something else. That's what we did with the edit distance, right? That's what we did with the probability calculation of the sentences, language modeling, and etc. We are going to do exactly the same thing. It's like the movies, right? At the beginning, the hero of the movie is under a very tough situation. It seems like impossible to solve that problem, but at the end, it is always the happy ending with the American movies, right? Nobody good dies at the end of the American movie. It's like an American movie, okay? At the end, we are going to solve it, and it's going to be perfect. Everybody is going to be happy until the final exam, right? In that final exam, nobody will be happy. Okay, so let's look at this problem. The problem is, again, we are going to use the problem is, okay, we solved the problem formula wise, we solved it, but we don't know how to make this operational again. We don't know how to come up with this set of tags. Okay, let's try to understand what these probabilities are. This one is called transition probability. Transition probability. And this one is called observation probability. Okay? These are standard terms in the literature of hidden Markov models. Hidden Markov models, okay, is defined this way. You are going to give me two types of probabilities. The transition. What is the probability of having an article after a noun? What is the probability of having a verb after a pronoun, and etc.? Observation probability is what is the probability of, okay, given this tag, what is the probability of having this word, such word, WI. Those are the observation probabilities. If you can calculate those, hidden Markov model says that, okay, I am going to give you a nice way of finding the maximum probabilities. That's what we're going to look at. But before that, let's look at this example. That flight, the yellow hat, okay. Okay, that flight, the yellow hat, so we expect probability dt and probability jj dt to be high, but dt jj to be, but what is dt jj? Given the adjective, right? Given the adjective, what is the probability of having a determiner after that? Right? That's what it says. Probability of dt after the adjective. How about this one? Given the determiner, what is the probability of having a noun? That's what it says actually. Calculate this one. Question for you. Sometimes I put a count in here. Sometimes I put p. Which one is correct? P is correct actually. Right? P is correct because that's the Bayes formula, right? Bayes formula doesn't talk about counts. Bayes formula talks about the probabilities. How come I put counts in there? How come?
We don't know the probability yet, maybe.
Yeah, but that doesn't make it right. I mean, if this one is equal to this one, then I should come up with an explanation. How do you calculate this one? Count of TIs. How about PTI? It is the, right? Count of TIs over count of all words, right? How many words do you have? How many of them are T1, TI, right? Well, I'm going to do the same thing here too. So it is, I'm going to divide them by the count of words. So they cancel each other. So these two things turn out to be exactly the same thing, okay? Doesn't matter if you are, I mean, the count of something is not the same as, of course, probability is between 0 and 1. But in this case, since those PWs will cancel each other, then I'm going to have this. Okay, so I can calculate it, and it looks like, well, this is intuitive. This is expected. After the determiner, okay, after the determiner article, that man, that building, that car, this car, etc., I expect a noun, right? 50% of the time. Okay? Well, then you will say, what else could there be? Maybe there is an adjective. That yellow car, right? In that case, it's going to be adjective. Okay? So I can calculate this, no problems. These are the estimations. Since we are using only 2 grams, right? Our corpora should be good enough to calculate it. I'm not trying to calculate 5 grams or 6 grams or anything like that. 2 grams. That's enough. Okay, so 2 kinds of probabilities. One of them is transition probability. What is the probability that noun comes after the determiner? Okay, these are the transition probabilities. The other one is, okay, word likelihood probabilities or observation probabilities. Okay, this one, given this tag, okay, given this tag, how many of them is okay? Well, that's a very unfortunate example, but okay, given this tag, how many of them is? The second is, okay? This is the calculation. It says VBZ. What was the meaning of VBZ? VBZ is to be verb in the, what is VBZ? Let's go there. To be verb in the third singular, VBZ. VBZ is this verb, third singular presence, that's eats. Okay? Eats. Oh, well, this is a surprising result, right? Eats, runs, etc. So to be is. So it looks like if something is marked as VBZ, 50% of the time that word is. Where is it? Where did it go? Yeah. Right? So interesting statistics. Okay. Well, I mean, we have to believe it, right? This is statistics. They counted it. So I can calculate both the transition probability and the word likelihood observation probability and multiply them, and we will find the result. Let's look at this one. Okay, the secretariat, remember what the secretariat is? Secretariat is a horse, is expected to race tomorrow. Okay, and people continue to inquire the reason for the race for outer space. Okay, I mean, in this case, this is a verb race, this is a noun race, right? How do we pick the right tag? Okay, this is, by the way, this is how you show the HMM Middle-Markov model in a graphical form. Okay, in a graphical form. Usually these are transition probabilities, right? Probability of transition. These are the word likelihood or the observation probabilities. So I will multiply this one, all of them, right? All of them to find the probability of P given the tags, the probability of having these words. Okay, so let's look at this one. I think it is race to race. Okay. Let's look at these two. The difference between these two is, okay, this is noun phrase, noun. Sorry, not noun phrase, noun. This is verb, okay, VBZ and VBN. 2 is there. This one says that this is a verb, this one says it's a noun. So, I mean, the probability of this one, given these tags, probability of W's, right? Or just do it. Given these words, probability of W's, and given these words, probability of W's, calculations are going to be very, very similar. The only difference is W's are the same, tags are the same. The only difference is between these two. So see, this arrow, this arrow, this arrow is as marked as bold arrows. They are different. Okay? Why are they different? Because this one is going to calculate probability of given to the transition probability of VB, right? And this one is going to calculate probability of VB and R. What was an R? Adverb, right? Adverb, right? And what is this? Tell me what this is. P given what?
VB.
Exactly, VB and race. Okay. The rest of it is the same. Okay, what is this? Probability of given to, right? Well, it will be exactly the same as this one is going to be exactly the same as this one, right? And this one is the same, this one is the same. The only different stuff is this guy, this guy, this guy. Okay, let's do it here. Probability of given to n, okay. Probability of given n, nr, and probability of given n race, right? Okay. So 2VB, 2NN, NRVB, NR, right? Is that correct? No, this is not correct. This is NRVB, right? Given VB, the probability of NR. Okay, so let's calculate 1, 2, 3, 4, 5, 6 probabilities and multiply these 3 together. How am I going to do this 3? Multiply these 3 together, the red ones. Also multiply the green ones together. See which one is a greater value. Whichever produces the greater value is going to give us the answer. The upper one is correct or the lower one is correct. Which one do you think is going to be? Which one do you think that is going to be larger?
First one.
Yeah, the expected to raise tomorrow. It is verb, right? First one. Okay, but which one do you think is? Which one do you think is larger? This one or this one? Given VB, how many of them are race? Given NN, how many of them are race?
I mean,
First one and
it depends on the corpus we use.
It is brown corpus. It is regular, common English, everyday English corpus.
I think first one is more likely.
Really? Out of all the verbs, race is more, out of all the nouns, race is, let's see, I don't know. Let's see what happened. Okay. It looks like, yeah, well, this one is better yet. Again, this is statistics, right? This is larger. Most of the time, given all the nouns, race is happening more.
The verb has many conjugations.
What?
We just verbs have many conjugations, like not just phrase, but maybe all the forms of the verb
Maybe,
in
yeah.
total larger, but
But I mean, but there are different types of verbs, lots of different types of verbs. But there are different types of nouns. Well, you don't reason with the statistics, right? I mean, why do we do the statistics? Things happen, and after the things happen, we do some calculations, and maybe we can come back and you talk about the statistics, but we don't reason with it. I mean, there is no. We don't get to say, no, this shouldn't be happening, and etc. No, but it happened. If I use only the standard statistics by looking at how many times this race happened to be a noun, well, it is larger. But we are not doing that because this one is way smaller than this one, right? Two noun, right? Yeah, well, no, this one. Two noun, after two, having a noun is, where did it go? Okay, here it is. Given to what is the probability of having a noun is very, very small. See? Well, it is not, it doesn't say it is 0. It is very, very small probability, but once you see a 2, after 2 you expect a verb. Okay? 80% of the time. So there is like maybe 5 times more probability here, but this is more than 1,000 times, 100,000 times, 5,000 times. Is that correct? 5,000 times more probable. So if I multiply VB, okay, let's write the red ones. Red ones are this one. Red ones 2VB, right? 2VB is red, right? And VBNR is red. This one. Also VB race is red. Is that correct?
Yes.
And the green ones are the others. If I multiply green ones and the red ones, you are going to see that race VB, okay, the red ones, this one, it's the red ones, right? Red ones are very, very, very, very much more probable than the green ones. So we correctly choose the verb reading, not the noun reading. Remember what happened? Why didn't we multiply these values? Because it doesn't matter. It is the same thing. I mean, this one both says it is noun, and this one is VBC and VBN. Of course, in real life, how do I know that is a VBS or expect is? Of course, it is. We don't know in real life, but for the sake of simplicity in this example, I disambiguated race in this example. Okay, so I made it operational. I know how it works. The thing is that how am I gonna given this sentence, Secretariat is expected to raise tomorrow, how am I gonna find correct tags for each of the word out of the 45 tag set? That's what we are going to do. Okay, for that one again we are going to use the hidden Markov model. Any questions so far? Well, if there are no questions, let me take some 10 minutes of break. After the break, we will continue. Yoklamayı unutturmayın arkadaşlar. Yoklamayı çıkarmıştık. İşte unutturmayın bir sonraki derste. Unuttum çıkarmayı.
biraz korktum da şimdi yavaş yavaş kesilmiştir. Şey işte sigorta bölümünde o kısmı
Peki, tamam. Nasıl olur? Konuş, gözden
Gebze benim küçük olan büyükler şey yapıyorlar. Tabii sadece bana yansıtılmaz. Öğrenmesi çok zor oldu.
böyle şeylerde her şeyi kontrollerden gerekiyor.
Normal şöyle çalışıyormuş. Bir tane veri tabanı yapıyorlar işte. Onlar mesela hızlı dönüşmen diye. Nereden bir şey çeksin diye. Bu otomatikler yapıyor. Şunları yazılıyor diye. Devamlı şuradan şey yapıyor. Depoda katmak şuraya. Şey yok işte çok fazla işte bölümüne düşler.
Zaten öyle yani. Biraz kurumsallaşmış şirketlerde her şey, herkesin ayrı bir işi var.
Her şey isim.
Hemen
Bir kişi bana tek bekar. Bekardan aynı bekliyorum. Diğeri patron zaten şunu yapıyor.
Böyle kırmızı işte olmak biraz korkutuyor ya. Öyle bir standartlar olmaz.
Üstte olsam belki daha iyi kalır. Yani nereye yollayacağım.
Çünkü mesela test bir çocuk bana kontentin bekarına yollayacağım tam söylemiyor. Mesela canlı diye. Diyorum ki ne istiyorsun kardeşim? Söyle de yazayım. Sen bana vereceksin, ben sana vereyim.
Aynen. Kanka iki farklı dili yeni öğrenmiş insanlar gibi. Üstte sen ne ettiğini yani. Ben çok rahatlıyorum.
Söylemiyor ne kadar işte. Ben de biliyormuşum gibi düşünüyorum.
Ama şey değil mi? Üstelik kendimden orada bir şey gibi şeyler. Zaten okulda devam ediyorlar. Aynen. Ama o zaman konuşuyorum. Okan mesela şey kullanıyor. En kısa kullanıyor. Ben hiç yazmadım. En kısa şeyler kullanıyor. Güzel yapıyor.
Mesela 10 dakika zil oldu, standart oldu.
Bir de şu an çok yapay bir şey yapıyor yani. Kendi tanımını tanıttığı zaman öyle mi? İlahada tam tersini söyledi. Ve tam ya çok basit bir cevabı daha çok seviyorum.
Ben beni. Tamam, o yüzden diyorum ki yok kardeşim ben uzak. Ve iyi yaptım. Bayağı. Geçen yıl bu yazdığı yıldan geçti.
Ne olacak ya da bayağı iyi oldu.
Evet, ben mekanlar ne kadar getirdim. Yani psikolojik
Backend'de bir noktaya kadar.
Deli nasıl?
Ondan sonra
Var mı? Bildiğin her zaman gibi mi?
Her zaman
Bir şey kısmı güzel. Yani şöyle. O da
Çok şükür. Bu nasıl? Orta. Klasik doldurayım doldurayım. Artık yapay zekada bir şey çıkıyor. Sembolik almıyor değil mi? Zorlamadık mı? Çalışması bir kere. Çok mu? Algı nasıl? Çıtırından doldurulabilecek.
Anlamada dinlemede katılımda sorun yok. Sorun yok.
Adamlık görmüş.
Bayağı fazla şu an.
Sen şey
Başlamayı ya ne diyorsunuz ya? Şuraya geldim. Şarkıya
Şey var.
Başlasın.
Gözü yukarıda bıraksın. Her zaman. Her zaman gözü yukarıda. So hidden Markov models, first they define the problem, then we provide a solution to solve the problem. With the hidden Markov models, we have two types of probabilities: observation probabilities and the transition probabilities. Okay, so I am going to skip this. Let's look at this one, independent of what hidden Markov model is. Okay, let's say we have a finite state automata. Okay, it's a transition graph. We are trying to model the weather. Okay, we say that given any sequence of days. Okay, it could be a day, could be a hot day, cold day, or rainy day. Okay. And these are the probabilities of, for example, A22 is having a cold day after another cold day. This is A33 is having a rainy day after a rainy day. This A13 is having a rainy day after a hot day. Okay. If I know all these probabilities, then I can calculate the probability of having cold, cold, cold, rainy, rainy, rainy, cold, rainy, hot day, right? So if I know all these probabilities, okay, this is called a typical Markov chain, okay, Markov chain for weather. As you see, everything is observable, nothing is hidden. That's why sometimes we are going to call it hidden, not hidden Markov model, but observable Markov model. In this case, all I have is the transition probabilities. What is the probability of having a cold day after a hot day? Or what is the probability of having a cold day after a cold day? Okay, these are all probabilities that I can extract from our weather observations, like my weather observations, and nothing is hidden. Whatever I am observing is my state. Okay, these are my states, and those are my observations. Okay, and I can do the same thing with the words too. Okay, so what is the probability of snow being the first word of a sentence? It is this one. What is the probability of having white as the last element of a sentence? It is this one, right? So I can calculate the probabilities of the complete sentences. I observe the words. I know their transitions. This is basically P W I minus 1 P I pi, right? So just simple 2-gram modeling of the language. Okay, Markov chain for words. Again, everything is observable. Okay, everything is observable. Okay, so this is what I need to know. Markov chain, first order observable Markov model. Does anybody know about the Markov models? Did you see it somewhere else? I'm going to ask, what is the second order? Maybe you can. This is the first order model. What do you think the second order is? Second order is if I am trying to calculate Wi given the words Wi minus 1 and Wi minus 2. Now I am dependent on what happened before me and before that. Okay, so this is the if I can draw such a thing, this is the second order. If I need to calculate this one, this is the second order Markov chain. But this one is first order observable Markov model. First order observable Markov model. I am just looking at. I am only dependent on the previous one. Okay, I have these states from Q1 to Qn. Okay, and I have set of probabilities from A01 to ANN. How many probabilities are there? How many probabilities are there? There are n states. What?
N times n?
No, very close. It's not n times n, but because remember, I need this one and this one too. This one too. Or maybe this one, right? I need a start and n2, right? Beginning and ending of that 2. So it is going to be n plus 1 times n plus 1. Isn't that n plus 2 plus times n plus? No, it is not, because the transition is between the states, right? Okay, so that many probabilities. Each ij represents the probability of transition from state I to state j. Okay, and the set of these is the transition probability matrix A. So such a matrix. Okay. Current state only depends on the previous state. Remember, well, this is not exactly correct. How am I going to fix this? This is not exactly correct. I am going to fix it by putting a approximation sign there, because of course this is not equal to that one, because you are ignoring the my sequence before what happened to my previous sample. What happens before that? I am ignoring those. But that's the Markov assumption, right? That's the Markov assumption. Okay, so these are observable Markov model formal definition. Observable Markov model formal definition. In observable Markov models, okay, I can calculate the probabilities of such things happening. Probabilities of such things happening. A probability of a sentence using just 2 grams. If I am using the first order Markov model, or probabilities of weather happening this way, if I use the first order Markov chain. Okay, everything is observable. Somebody, okay, so this is the set. What is the probability of 4 consecutive rainy days? Okay, it is state is 4 consecutive rainy days. I will start with this one. It is A03, then 3333 and 34, right? So if I multiply all of those, it looks like the multiplication is, I guess this is 03, and this is 3333, and 34 is the same thing, and I get this. Okay, Markov chain for weather works that way. So let's look at this hidden Markov thing, HMM. This guy is a famous NLP researcher from University of Maryland, I guess. Yeah. Either he defined this problem or somebody making fun of him define this problem. So you are a climatologist, iklim bilimci, right? So in the year 2799, and you are studying global warming, and you like to know how was the weather in Baltimore in 2007. So these slides are very old, okay? And so you don't know the data, you don't know the weather, you don't know whether it is hot or cold or rainy for those days, the summer of 2007. But you found this guy's diary, günlüğünü bulmuşlar, and he take a note of how many ice cream bars he ate that day. Okay? Well, you might say that if the weather is hot, he ate maybe 2 or 3. If the weather is cold, that day he didn't eat anything or he just ate just 1. Okay? So that's our assumption is. Our job is figure out how hot it was. Figure out how hot it was. So that's where the hidden Markov model comes from. The observation is not your state. I cannot observe it in this year because I don't know how the weather is. All I have is how many ice cream bars that guy ate. Okay? It's exactly the same thing as I don't know the tag of my word. I don't know if it is verb or noun, that race, okay? But all I am observing is the word itself, okay? So that's where the hiddenness comes from, okay? So for Markov chains, the output symbols are same as states, but for hidden Markov models, the observable things are verbs, the words themselves. The hidden states are part of speech tags. For this example, okay, the observable things are the how many ice cream bars this guy ate. Hidden states are the weather state for that day, hot or cold or rainy. Okay. So, and this is the definition of the hidden Markov model. Again, I have n states. Okay, I have n states. I have n observations. States are hidden. I don't know what state I am in, but I have the observations. I have the transition probabilities between the states, and I have the observation likelihoods. Rehan, could you close that door? Sorry, I cannot go. Okay, I don't. My transition probabilities are, okay, again, like the probabilities that I told you. What is the probability having a verb after a noun, for example? Then the observation likelihoods, okay? Observation likelihoods are like, what is the probability of given this tag verb race? Okay, those are the observation likelihoods. For the Eisner case, observation likelihoods are going to be what is the probability of that day being hot if that guy ate 3 ice creams, because these are my observations. Okay, and remember this guy says that, okay, P3333. This guy says that what is the probability of eating 3333, etc. Okay, I can calculate it, but later I'm going to do, if I ate 3 bars and 3 bars and 3 bars and 3 bars, okay, what makes this sequence the highest probability in terms of weather? Maybe I'm going to say it's going to be a hot day, hot day, hot day, and hot day. I don't know the states, but I'm going to calculate it. Okay, good. So for the hidden Markov model, I have the states, observations, transition probabilities, and observation likelihoods. What is this spatial initial probability vector? Can you guess it? It is related to this one. It's a vector. Its size is n. Just a one-dimensional vector. Its size is n. So what does it hold?
Probabilities at the beginning?
Probabilities of initial, yeah. What is the probability of me starting with this hot day? Because there is no transition for the first one, right? What is the probability of a sentence starting with a pronoun or verb, right? Those are the initial probabilities. Okay? So if you have 1, 2, 3, 4, 5 things, then you have a hidden Markov model. Okay? So for that, okay, these are my observation for the Eisner task, that guy, the guy who ate the ice cream bars. Okay, he ate 1, then 2, 3, 2, 2, 2, 3, okay? And I like to produce this one, okay? What is the argmax of probabilities that produces this many ice cream for those days? And I can come up with such a sequence, okay? And this is the thing, okay? So let's read it. It looks like this is like same as the observable Markov model, but again, as I said, we don't observe the hot and cold days. We observe only how many ice creams I ate or that guy ate. So what is this 0.3? 0.3 is
Cold after hot.
So how do I calculate it? It is like P probability of having a cold after hot. How do I calculate it? It is, okay, count of hot days, right? Count of hot days, then count of cold days after hot days, right? That's how I calculate it. Okay? And this 0.4 is just opposite. This is hot after hot, hot after hot. Okay? So these are all what probabilities? Transition probabilities. These are transition probabilities. And how about this? This is P1, okay? Or pi 1 and pi 2, not P but pi. Pi 1 is 0.8 and pi 2. So tell me what is 0.8? Probability of a sequence starting with a hot, right? Okay. Well, I mean, I guess this is not a very intuitive vector. I would have said it is 0.5 and 0.5 because wow. Did you guys know why? Did you guys know they are smart? No, this is right.
This is summer.
Yeah, because it is summer, right? In the summer, probability of having a hot day is higher than the cold. So, given nothing, probability of having a hot day in summer is high, right? And that's why this 0.3 is smaller than, right? Going from hot to cold is a small probability, and staying in cold is small probability. Of course, I am not doing by intuition. I am calculating these for the summer days. And then I have these. How do I calculate this one? P1 hot. I calculate it, okay. P1 hot. Out of all the hot days, on how many of them I ate only one ice cream, or regular person eats the ice cream, right? Okay, so it looks like, by the way, these should add up to 1.0. It looks like, given the hot day, I know it's that day is a hot day, most probably that guy eats two or three ice cream bars. Okay, sometimes one, but never zero, right? How about this one? Well, it looks like this guy eats at least one ice cream every day, Doesn't matter if it's hot or cold. If it is cold, most of the time it is one ice cream person. Okay? Okay, these are my observation probabilities. Again, my observation doesn't tell me about the hot or cold days, but this is the best I can do, given all these observations. Doesn't matter what kind of application you have, it's either the part of speech tag estimation, or part of speech tag estimation, or cold day, hot day estimation, or what else? One of our students, PhD students, did this. Given the lumbar MRI, she did exactly this. Lumbar MRI image. Okay, good. Let me take this. Okay, good. This is an MRI image of somebody's back, lumbar region, this region. Okay, these are called discs. Okay, it looks like there is a herniation, fıtık, bel fıtığı. There might be, because this is the nerve channel that runs through behind your vertebra. Okay, if there is a herniation there, fıtık, it just it forms some kind of a pressure on your nerve channel and it causes pain. So what she did is, okay, these are supposed to be labeled. This one is, okay, L1 vertebra, L2 vertebra, L3, etc. And these are called L1, L2. These are the discs, okay? So somebody has to mark them. These are my observations. Given this observation, what is the probability that this region is an L1? What is the probability that this region is L2, etc.? Okay? She did exactly that, and it was a very novel application of the hidden Markov models, and she's still getting lots of references for that work. Okay, so these are L5, L4, L3. L means lumbar region, okay? Just the lower part of your vertebra. Intervertebral disc, and it looks like where is the this is a healthy vertebra, I guess. Can I see a bad? This is healthy too. Well, I am just making it up. I don't know. Oh, this is bad, right? Okay. Oh, this is bad. Oh, this is this guy is in pain. This one, it is all herniated. It is putting lots of pressure. Anybody having any bel fıtığı problems?
Neck.
From the neck? Yeah, this is what's happening. Okay, so you should know hidden Markov models, right? You know. Okay. So what I'm saying is that, remember what I told you? I mean, when you are taking this course, don't take it as like I'm going to do this in natural language. Of course, that's one of the main purposes. But if you have any one-dimensional data, like this vertebra, human vertebra is one-dimensional, right? You can use hidden Markov models, okay? Usually we try to assign these kind of labels to one-dimensional data, and those labels are only meaningful to human beings, not the real thing, right? I mean, there is no such thing as L1 vertebra in the natural world. We just give that name to that, right? I mean, that vertebra exists regardless of we are giving a name to it or not. But without giving those names, our brain doesn't work. We need to give those kind of names. Like there is no hot day or cold day. Those are our models. Or there is no verb. There is no noun. Those are the things that we conceptualize by looking at the natural thing, natural language. Right? So hidden Markov models are used for that kind of purpose. Any one-dimensional data, they can be usually applicable. And if you have one-dimensional data, then think about hidden Markov models. I gave you two examples, one for the toy problem of ice cream, which is not that useful, but the other one is very, very useful. It is It is being used. It is being used. Okay, so the transition probabilities and observation likelihoods. Okay, let's look at this one. This is nice, right? So I have the transition probabilities between these three part of speech tags, verb, noun, and to. Okay, and these are my observation probabilities. Given to, what is the probability of having aardvark? Or what do you know what this is? It's an animal. Okay, usually in the English dictionaries they start with this word and it ends with this word, right? Okay, and I need to. I mean, this probability tables, this table, this observation table is very large, 40,000 lines in here, and 40,000 line there, and 40,000 line there. Okay, but the transition probabilities are not much. How many transition probabilities do I have for the 10 pen tree bank? For the 10 pen tree bank, we have 45 tags, right? It is 45 times 45 or 65 times 65 transition probabilities. Okay? So, I defined the hidden Markov model. Now I'm going to look at this decoding. Decoding is, given these words, okay, find me the exact set of tags that makes this expression maximum, arg, max, p, such and such. Okay? If you try to iterate over everything, that's going to be exponential time. We don't like it. Not a good idea. Luckily, dynamic programming, last seen in chapter 3, with minimum edit distance, we see that, right? It's going to work. This is what we are going to do. This is the Viterbi algorithm, or the dynamic programming algorithm. This is the guy who used this algorithm for some one-dimensional data using the hidden Markov model. But I am not going to look at it at this moment. I am going to show you this. I think I did that already in our last lecture. This is what we are going to do. I want to raise. I like to assign tags to this sequence. I want to raise. In our word, there are only 1, 2, 3, 4 tags. A word can be either noun or to or verb or what is PP? Pronoun. Okay? It could be either one of them. Okay? And I am going to add 2 more tags, dummy tags, and start. Okay? I know the state for this one is start, and I know the state for this one is end. Okay? And I am going to assign some probabilities to these links, and by following the link with the highest probability, I will try to reach this end from start to end. It's exactly like the minimum edit distance. Okay, let's look at this one. What does it say? It says that the cost of this path is, okay, cost of this path is the probability of seeing a verb after start, okay, times the probability of start. Probability of start is 1.0 for that one. Let's look at this one maybe. This one is, okay, this one is probability of seeing a verb after a verb times V12, okay, whatever you collected up to this point. Okay, so I keep collecting these values, but for this one I multiply it with probability of seeing verb after a verb, that's the transition, times the probability of this observation. Given VB, what is the probability of want? Observation probability. Okay? So if I keep doing this, so this is my table. First I fill in this column, then I fill in this column, then this column, and this column. Then after that, I fill this column. And whatever path gives me the maximum probability, I pick that path, and that's going to give me, okay, I assigned, I think it's going to be like this. The optimal path is going to be pronoun, I is pronoun, want is verb, to is to, and race is a verb, then this. So this red path is going to produce the largest probability. Okay? Again, so how much time did I spend? It is 1, 2, 3, 4, 5, 6, n plus 2 times, I need to calculate this one, times number of tags plus 2. Okay? Number of words plus 2 plus number of tags plus 2. Way better than exponential time, n to the n or n to the t. Okay, linear time. It's linear time. So let's look at this Viterbo algorithm actually. So the Viterbo algorithm says that give me your observations, your words, and state graph of length n, this graph, okay, without any values marked yet. Okay, initially for each state s from 1 to n, do, okay, for each state s from 1 to n, do this initialization step. Okay, Viterbo S1 and S1. So I am going to fill in this one. Okay, fill in this one. It says that, remember, A's are transition probabilities, B's are the observation probabilities. Okay, multiply this A0S with BS O1. O1 is the first observation. Okay, so I did that. That's what I did here. Probability of, this is the transition probability, and this is the observation probability. Okay, put them together, I initialize it, then start doing this. Time is from 2 to t, s is from 1 to n. S is doing this, S is doing this, this, and this, and T is doing this. So it's two nested loops, 2 to T and 1 to N. Okay, T times N is the cost. I keep back pointers so that I know how to come back. Okay, how about this one? Can anybody explain this to me? What is this? As S prime is from 1 to n, what does it say? It says,
Take maximum of each step.
say it again.
Take maximum of each step.
Take maximum. Okay, it's kind of like this. To calculate this one, try to come to this position either from here or there or there or there or there, right? Try each of them one by one. Choose the one that produces the maximum, right? Choose the one that produces the maximum from 1 to n. So it is testing all of them one by one. And it says that if I am coming from there, I need to multiply with this observation probability, transition probability, and then with this observation probability. Maybe they should have, okay, maybe they should have just do this, right? Because this one doesn't change for this t, right? T stays the same. I mean, they don't have to multiply with b, s, o, t to get this maximum value. Okay? So it is finding the best assignment from 0 to step number n, or step number t, sorry, step number t, and then it continues on top of it. It's just filling in like we did with the edit distance. So it is doing this with column by column.
It is recursive and two nested for loops.
Two nested for loops and one for the, I think it is two nested for loops, and there is another loop to pick the largest one. So it looks like it is n to the power 3 or something, n times t times and n squared times t, right? Something like that, because there is one n in here. Okay, so that's the Viterbi algorithm. That's the summary. Okay, create the array with columns corresponding to inputs and rows corresponding to possible states. Columns are inputs, input, input, input, input. Rows are the your tags. Which one? Okay. Sweep through the array in one pass, filling the columns left to right, using our transition probabilities and observation probabilities. And dynamic programming key is we need only store the maximum probability path to each cell. Okay. So again, it is not exponential complexity, but linear in terms of t, or the number of inputs. Okay, so how do we evaluate? Okay, we did that. Okay, we use the first order hidden Markov model. Question for you: if I wanted to use second order hidden Markov model, how would you change this graph? This is first order hidden Markov model. Okay, this is first order hidden Markov model. How would you change this picture if I like to use second order hidden Markov model?
We need to group last two words and an arrow to them.
Yeah, exactly. We need to group last two assignments, right? The part of speech tag assignment. And so how are you going to group them? I'm going to do this then. This NN should be NN, NNTO, NNVB, NNPP, right? So each of them should be replaced with n number of them. So number of states in each column will be square of this number. It's going to be 16 plus 2, right? It's going to be 18 now. So it increases the number of elements, number of tags or tag assignment in each of those rows. Yeah, but it will be a little bit better than your first order hidden Markov model. Still linear time in terms of number of words, but quadratic time in terms of number of tags. Okay, so it can be. Second order hidden Markov models work better than the first order hidden Markov models as expected. So it doesn't matter how you do it. Okay, once you assign your tags to your input data, I need to measure my results, right? I need to measure how successful I am in terms of assigned tags. So how do I evaluate it? I mean, this is the requirement of any science area, any science branch, right? Or engineering branch. If you do something, you need to measure it. How do I measure it? Well, maybe you can say that, okay? Maybe you can say that. Look at the confusion matrix, okay? What's the confusion matrix? It's going to give you this. For a tag that has to be in, okay, 20% of the cases, I assigned adjective to it, and 70 sorry. It's not going to, well, these are not the percents, okay? So this is a normalized version of it. Let's say I have a total of n errors, okay? I have a total of n errors. Out of those n, 0.2 is this error, and 0.7 is that error. And it looks like the highest error I am making is this here. Okay? I am confused between nouns and adjectives. I like to say it's a noun, but I'm saying it's an adjective. How about the opposite? Yeah, opposite is high too, this one. Okay? So, estimate this confusion matrix. Of course, you like to see all zeros in here, right? Or very small numbers. And calculate the number of errors you are making. That's one thing. The other thing is that what kind of errors are you making? I mean, are you doing this or that or okay? Well, there is no errors such as I am not confused about a verb being an adverb. Okay? They are not confused much. But this one is red. Okay? This one is very, very confusable. You calculate it. And human sealing problem is there. Okay? Typically accuracy reaches 97%, and nobody should expect 100% accuracy, because as I said, even the top experts, they cannot agree on some of the assignments, tag assignments for some of the words. Okay? So that's the typical problem with NLP data sets. Once you start seeing 96, 97%, you don't work on that problem anymore. Okay? You say that I am overfitting to this data now. Okay, I am overworking on this data. I need to find a more challenging data set so that the top performing algorithm does maybe at most 90%. More than 97%, 98% doesn't make any sense. That doesn't mean that nobody is going to report 100% accuracy. If somebody is reporting 100% accuracy, they are doing something wrong. It is achievable, but the fact that you achieved it doesn't mean that you did a good thing. Okay? You overfit it. That's it. Okay, so in summary, I told you about part of speech, the tag sets, and I showed you two ways of assigning part of speech tags. One of them is the rule-based method, which is very limited in terms of scalability. Then we have the hidden Markov models. Okay, and I showed you how to handle the first order hidden Markov model using dynamic programming again. Good? Any questions? Okay, if there are no questions, I am going to start a new chapter now. But before going to the new chapter, let me show you the new chapter name. Okay, remember what we were doing? We looked at the morphology, okay, how the verbs are formed, the verb structure, word structure. Then we looked at the part of speech. How do I classify each word in a sentence? Now we are going to look at the grammar, the whole grammar. What is the function of the words or word groups in a sentence? We are going to look at it. So we are going to look at this formal grammars. Okay? But before that, let's take some break. After the break, we will continue. Part of speech. Part of speech. Cümlenin öğelerine benziyor, evet. Ama
bir önceki kelimelerin
hayır bu cümlenin öyle değil, bu gramer bayağı bildiğin. Cümlelerin öğelerine, ya cümlenin öğelerine benziyor esasında. Ne koskocaman bir yeri çekip buna yüklem falan filan der. Benziyor birazcık ama tam da değil. Arkadaşlar şu arkadaki şeyi açabilir miyiz camları? Yoklamayı yeni unuttum. Dersin sonunda değil, başında hatırlatacaksın.
Şimdi benim aklıma geldi.
Dersin sonunda değil, başında aklına geldi. Yoklamak lazım. Geldi mi? Hayret bir şeysiniz ya. Gelmedi tabii. Söylemediniz ki. Evde yoktu herhalde. Ah baba, oğlum burada. Ah, iyi mi yoksa? Neyse. Oldu.
geliştir. En son en kötü değil. En kötü yazıyorsan da en son participate istiyorsan accept diyoruz. Hani şeyleri çizmek için karşılığı olmaması için değiştir. Karşılığı olmaması için birlikte artık. Şu çizimler Spice'de şey krem hatta iyiye yaklaştırıyor. Yaklaştırıp değil. Şu kısmı uzaklığını gözünden de şunu yani şunun yüksekliği götürüyor. Bu aynı. Örneğinden bilen hepsi. Bütün sebebi boyutun yüksekliği Ya şöyle oldu, fiyattan çıktık işte. Bizim dönem, bir de bizim dönemler çok zordu ya. O hiç böyle çıkmadı. Yani şu nasıl yaptım, ben nasıl yaptım.
Hemen başlıyor. Buraya sarkıyorsun, buraya sarkıyorsun, birbirine ayrılıyor bir şey yapıyor. Sonra 12'de 9 yazmış demişler.
Çalışmayı daha çok iyi. Onlar çalışmayı
İşte çağrı çok önemli sırada evleniyor. Seçiyorsun, diğer simayı yapıyorsun.
Çalışmaya
Ben kendimi ikna etme süreci, masa yönetim süreci.
Burayı yaptıktan sonra polisi yapıyorsun. Sadece beyan yapıyorsun. Her şeyi alıyorum orada.
sabah yapılacak başlıyorsa akşam da tutacaklar yakınlarda.
Çok iyi merak
Bunlar zor yani.
Arkadaşlar ben ne zamandır yoklamam böyle ya. Neyse. Siz ben bunun içinde falan bir arada şu gelmeyene de bir çizgi atar mısın ya? Okay, formal grammars we are going to do parsing. Okay, context-free grammars. We are going to look at this Chomsky hierarchy. Anybody knows? You know the Chomsky hierarchy from the programming languages course that you took some time ago during your undergrad years or maybe last year. Okay. So by syntax, okay. Syntax for us is how the language works. Okay, the rules of words coming together in that specific order. Okay, what should I say after this word? Okay, according to the language rules, you might say that. Well, we have been doing this already using the statistical language modeling, This is not statistical language modeling, okay? This is formal, rule-based language modeling, and it is different than the statistical language modeling. Another way of modeling the language. Okay. So why should I care? Well, I care about the syntax because I need to check if the grammar is right. Or for the machine translation, I need to do, let me show you one example, grammar, okay. So this one, a sentence, an English sentence, I prefer a morning flight, okay. English grammar says that some type of sentences are composed of noun phrases and verb phrases, okay? And a pronoun can make a noun phrase, and I is a pronoun. Verb phrases sometimes are verbs and noun phrases. Verb is a prefer here. Noun phrase is a determinate and nominal. Okay, nominal is a form of noun, okay? A general form of noun. And it can be defined as like recursively. See, nominal can do nominal noun. And this nominal can do a nominal noun again. So it is like morning flight, early morning flight. Okay? Expensive early morning flight. See, I can make it as long as I want. Okay? So you need some recursivity. So I have it, right? I have it. This is a language that does subject, okay, verb, object, SVO language, okay? Subject, verb, object language. Turkish is subject, object, verb language, right? So if I like to translate this sentence to Turkish, I need to parse it like this, extract the parsing tree like this, and I produce a parse tree for Turkish, but I am going to switch this verb and noun phrase. I am going to interchange their positions like ben bir sabah uçuşu tercih ederim. Right? Ben bir sabah uçuşu tercih ediyorum. So the prefer goes to the last. How do I know that? Okay, because I parsed it. Okay, I know that this part is the verb part. So of course everything is not as simple as parsing it and producing the parse tree for Turkish, but okay, machine translation requires parsing. I am not saying that the Google Translate works this way. Google Translate definitely works using the statistical machine translation or deep learning based machine translation, not this kind of machine translation. But again, since this is a course at the beginning of the semester, I talked about it, right? I said that I'm going to tell you about the new techniques and the old techniques too. And this is a classical technique to talk about the syntax of the language. So machine translation definitely needs it. Information extraction definitely needs it. For example, when you ask a question, what city is the capital of Turkey? Okay, you need to parse that sentence and find the subject of the question itself. Okay, capital of Turkey, and you find that information in your database. Or question answering, you need to answer, is it a question sentence or a regular imperative sentence or a statement sentence, etc. For all of those, we need parsing. Okay, we need grammar analysis. So we are going to talk about the syntax thing, constituency, gruplama, maybe in Turkish, grup haline getirmek. Constituency is how the words come together. Still, we consider them as part of the sentences. That's the constituency. We are going to look at those. Then the grammatical relationships between those constituencies. Okay, we are going to use this formalism context-free grammars, because for context-free, okay, you know the Chomsky hierarchy. Context-free grammars are above the regular expressions in terms of their expressibility. Okay, but they are lower than the context-sensitive grammars or free grammars. Okay. We like context-free grammars because they can hit the nice balance between expressibility plus the parsability, availability of the algorithms for these kind of grammars. Of course, with the three banks, we are going to see if we are doing right or wrong. In terms of evaluation, we are going to look at those. So let's look at this constituency thing, okay? Constituency is basically, okay, groups of words within utterances can be shown act as a single unit, okay? So we are not talking about a single word right now. We are talking about group of words functioning as a part of the sentence, like this one. Okay, like the one here. A morning flight is a constituency group of words, and I call this a noun phrase. A noun phrase could be a noun. Flight is a noun, but a morning flight is a noun too. Okay? So this is the constituency. How do I understand it's a constituency? Because it can act like a noun. I prefer a flight, or I prefer the morning flight. So I can replace them with each other, okay? Or sometimes you have the verb phrases. So this is a prefer a morning flight is a verb phrase, right? Or verb phrase could be a direct verb, like what can I say instead of I run? Just run could be a verb phrase, okay? So instead of having all these groups of words here, I can replace the whole thing with a single verb like run, okay? So constituency is an abstraction of how the words come together and function as part of a sentence, okay? So in a given language, these units form coherent classes that can be shown to behave in similar ways in terms of their internal structure and in terms of how they behave with the neighboring structures. Okay, a constituency such as a noun phrase has an internal structure. Also, it has relationships with the other structures in the same sentence. Okay, so the internal structure, for internal structure, a noun phrase usually can be said as, okay, a determiner plus noun. Or there are many other ways of doing the noun phrase. This is the internal structure. Or noun phrase is nominal noun. Okay, nominal noun. So I am defining some kind of a internal structure. To become a noun phrase, you need to follow this internal structure. But there is this external behavior too. Okay, we say that noun phrase and verb phrase. Noun phrases come from before the verb phrases. So that's the external behavior. Within the noun frame, I have this internal structure. For outside, I have these kind of external relationships. Okay, so that's the kind of definition of the constituency. And this chapter will deal mostly about how the constituencies are defined internally and how they interact with the other constituencies. Okay, for English it works very well. For Turkish, unfortunately, it doesn't. For Turkish, we don't use these kind of rules because these are order dependent, right? Determiner, noun, noun, determiner, etc. For Turkish, ben sabahları koşarım, sabahları ben koşarım, ben koşarım sabahları, ben sabahları ben koşarım. They all are acceptable and they all have different meanings. Okay? They are all parsable, right? They are all valid orders. Okay? So, unfortunately, the Turkish constituency is very, very different than English constituency. That's why we don't like these kind of parsing formalisms for Turkish. We have for Turkish, what we have is dependency parsing, and we are going to talk about it at the end of this chapter. Okay, good. Any questions so far about what we are going to do? What? It's coming. So that was your question? Okay. Okay. So all of them are here are noun phrases, NPs. What did I say? A sentence for English is noun phrase and verb phrase. Noun phrases could be as simple as they, or it could be the reason he comes into the hot box. Okay, it could be as complicated or more complicated than that. Okay, those are noun phrases, and as I said, they have internal structure and they have their external relationship with other constituencies. Okay, grammars and a constituency, and grammars basically, these kind of grammars basically tell you how the constituencies are formed internally and how they interact with each other. Okay. For that, we are going to use context-free grammars. And for context-free grammars, let's talk about them using the regular Chomsky hierarchy. So let me give you one context-free grammar, and we are going to come back to Chomsky hierarchy and see what's happening in there. Let me show you one. Okay. Very, very simple grammar. Very, very simple grammar here. L0 grammar. Okay, very primitive grammar. A sentence is noun phrase followed by a verb phrase. A noun phrase could be a pronoun or proper noun or determiner nominal. And nominal could be nominal noun or noun. The recursivity comes here. So this context-free grammar could be recursively defined, and that's the power of it. And we have that power in natural languages too. Okay, in natural languages too. And that's the noun phrase. In English, noun phrases are more complicated than the verb phrases, and this is the verb phrase. A verb phrase could be a simple verb, and depending on the verb type, okay, verb noun phrase, prepositional phrase, or verb prepositional phrase. Verb leaving on Thursday, right? Prepositional phrases on Thursday. Noun phrase, prepositional phrase, leave Boston in the morning. Okay? So not all words behave this way. Some of them could be in any form. Okay? Some of them could be only this form, and etc. And this is the prepositional phrase from Los Angeles. Right? So very simple grammar. Using this grammar, I can parse sentences like I go, right? How do I do that? Noun phrase and verb phrase. From noun phrase to pronoun, and pronoun is I. From verb phrase to verb, and verb is go. I go. Okay? L0 grammar. So this is a context-free grammar. In context-free grammar, I have these non-terminals. These are called non-terminals. And these are terminals. Our words are observations and they are terminals. Our words are terminals, and they are our words. These are non-terminals, and I have my rules. Okay, these are the rules. Basically, that's it. Okay. So, what is the context-free grammar? Context-free grammar. Let me show you the Chomsky hierarchy, and I'm going to. Okay. Chomsky says, this guy, 1956, he had this theory, and this guy might be alive. Is he alive?
Yes.
Really?
Yeah.
We are really in Turkey, we are really in trouble with this guy. This is the guy who talks about the clash of the civilizations. Western civilization is better than the Eastern civilization kind of guy. So he's 93. Well, he's not going to die. So I have been teaching this class for the last 10 years and he didn't die. So we can assume that he's not going to die. So he's a philosopher American linguist, philosopher, cognitive scientist, historical essayist, social critic, and Turkey's enemy, political activist. Okay. Does he still talk? I don't know. The Clash of the Civilizations, I think he said that, well, in maybe 1970s. Okay. So this guy in 1950s said that, okay, not just himself, some other people too. They came up with this hierarchy. Where did my hierarchy go? Yeah, okay, here it is. Okay, any formal language, okay, can be specified using one of these types of grammars. Type 3 grammar is the most restrictive one. Those are the regular expressions or finite state automata. Let's look at them, what those are. Type 3 grammars are the regular languages. Such a grammar restricts use to a single non-terminal on the left-hand side. See, singular non-terminal on the left-hand side. Left-hand side, let's say this one, A. What is this? Can I write on it? I think I can. Yeah. A on the left-hand side. Okay. A single non-terminal on the left-hand side and right-hand side consists of a single terminal, possibly followed by a single non-terminal. So A and B. That's it. Okay. This is a type 3 grammar, and you can't do any better than that. So you cannot say A, B, C. Okay, you can't do that. Okay, because C is a non-terminal or terminal. B is a non-terminal. B is a non-terminal. C is a non-terminal. Capital letters are non-terminals. Small cases are terminals. You can't do that. That's why using a regular expression, I cannot balance my A plus 1 over 7. I cannot balance my parentheses using a regular expression. I mean, I cannot count the number of parentheses that I opened because I can say that on my left and right there should be a parentheses, right? I can't do that. So type 3 grammars are like that. Regular expressions are doing, I think they had a small, yeah, okay, good. So with regular expressions, all you can do is this. A terminal followed by a non-terminal, that's it. Remember our sheep language, kuzu dili, right? I can do that by doing this, right? As sentence is something BA, A is either A or AA, right? Okay, so this is a type 3 grammar or regular expression. When I move up to context-free grammar, on my left, there is only one non-terminal. On my right, there could be anything. Okay, it could be as like this. It could be parentheses as a terminal, then non-terminal, then terminal. Or it could be parentheses A plus B, parentheses, etc. Any combination of terminals and non-terminals on my right. Okay, on my right. So this is context-free grammar. And all of our compilers, they work as like context-free. They work on languages, formal languages defined in context-free grammars. Okay, our regular expressions, which are defined like that, yeah, they are very useful in terms of shell programming and that kind of stuff. But for a programming language, formal programming language, we use context-free grammars. It works that way. And then on top of it, well, there is a very nice algorithm, non-deterministic push-down automata. It works very well with context-free grammars. That's why our compilers are very, very efficient. They are very fast. They run in linear time in terms of number of tokens that you have in your program. Okay. On top of context free, we have the context sensitive grammars. On context sensitive grammars, I have this. You can say that for A, I have this alpha, gamma, beta. Okay. But this A has to happen between alpha and beta. That's why it is context sensitive. This A has to happen within this context of alpha and beta. Okay? This one doesn't define any context, but this one defines the context. So it looks like for context for this one, type 1 grammar, okay, I need a non-terminal, okay, a non-terminal on the left side, but around the non-terminal you can have anything you like. Okay. When I move to the top grammar type 0, no restrictions at all on the left and on the right. You can have any combination of terminals and non-terminals. So for chapter about the word structures for morphology, we use regular expression finite state automata. For parsing sentences, now we are going to use context-free grammars. And not this chapter, but in the next chapter, next week maybe, I'm going to give you a nice dynamic programming based algorithm to do this context-free parsing of sentences. Okay? So, good. Okay. So let me move back to my slides. Okay, we talked about the context-free grammars. Okay, with the context-free grammars, I have the terminals, I have the non-terminals. Terminals are the words for now. Well, punctuations are the terminals too. For the non-terminals are the things that we define. Okay, like the sentence and noun phrase and the verb phrase and etc. And we have our rules. Rules include non-terminals on the left, on the right any combination of terminals and non-terminals. Some NP rules, non-phrase rules, non-terminal, what did I do? Okay, non-terminal, and non-terminal. On the right, again, these are two non-terminals, one non-terminal, and there is an or, either this one or that one. Okay? Together, these describe two kinds of NPs, and we define a nominal. You see this nominal thing? This recursive thing? Okay? So this recursive thing happens only with the noun phrases in English, I guess. As far as I remember, it is like that. Okay, good. So we looked at this already. I guess of course, this doesn't parse any question sentence, right? Is there a morning flight, right? Is there a morning flight? Doesn't work like this because it has to start with a verb, right? Verb phrase doesn't work in this case. This is only for statement sentences. I want a morning flight. It is not imperative sentence or a question sentence. It's like a statement sentence. Okay. Like the finite state automata or finite state transducer, we can use this grammar to produce sentences. Like I can say, okay, I started with, for example, noun phrase and verb phrase. Now I can use any of those rules to move one below, then one below. I can add anything like that. And at the end, I obtain a sentence that obeys the grammatical rules of the language. Okay, that's the generativity. Of course, I can produce I goes, right? I can produce too. which is against the rules of the language. Why? Because there is a subject-verb agreement in English. We are going to ignore that problem for now. I can do it by multiplying these rules with the plurality sensitive rules, okay? Singularity, plurality sensitive rules, but I don't want to do that right now. Let's not make things complicated for now. Okay, so derivations are like this. We talked about it. Okay, this is a context-free grammar definition of it. A set of non-terminal symbols, okay, like the sentence, noun phrase, verb phrase, etc. And terminal symbols, those are the words from the dictionary and including the punctuation. And a set of rules like this, context-free grammars. And beta is a string of symbols from infinite set of strings. See, sigma is the set of terminals, n is the set of non-terminals. I combine them, and star means that 0 or more times, any times, okay? And S is a designated star symbol. Usually we read as a sentence. And parsing is the process of taking a string and finding out a grammar. It takes the string and the grammar and returns a parse tree for that string. It takes this grammar, it takes this sentence, I prefer a morning flight, and it produces this parse tree. Once I have the parse tree, I do whatever I want with it, including the machine translation. Okay, that's called parsing. Okay, so having said that, let's look at the basic English grammar. And unfortunately, I won't be able to show you the corresponding Turkish grammar because, as I said, Turkish grammar is very, very fluent, very, very. Turkish is not, as I said, order. Well, order is important, but any type of word ordering is a meaningful sentence, as has a different meaning. That's why this type of constituency-based grammars is not suitable for Turkish kind of language, Turkish kind of languages. Okay, so let's go back to English. English grammar fragment. I have sentences, noun phrases, and verb phrases. Okay, we are going to look at them, and we are going to look at the verb phrases. Sentences, okay. Declarative sentences, a plane left. I'm just stating something. Imperatives, just giving you an order, leave. Okay. Yes, no questions, did the plane leave? Or WH questions, when did the plane leave? Okay. So I'm not saying that these are all the 4 types of sentences of English. There could be even more, but I am not going to look at it. I read somewhere, I forget where I read, somebody put together the English grammar rules together, 600 pages of English grammar rules, like these. Still, they can cover 95% of the sentences, parsable. Still, 5% is not modeled using this grammar. Okay? So, again, I'm going to repeat it. These are natural language, natural things. Our rules, they are not powerful enough to explain them, okay, grammar rules. And the grammar is not the natural part of the language. It is something that we make up, okay, that the human beings making up to explain the language. That's why it's a very bad idea to teach the grammar of a language to a foreigner first, okay? That's what they have been doing to us. They teach the grammar to us first to learn the English. Then later we try to speak the language and we can't. No, that's not the way. We should learn the language like the children, right? They learn the language before, then after that they learn the grammar. Okay, so as I said, I'm not arguing that these are the only ways to form sentence of an English. sentence of the English language. Okay, so these are the sentence types, noun phrases. Let's look at these noun phrases, how they are. Okay, let's consider the following rule in more detail. Noun phrase, determiner, nominal. Okay, determiner, nominal. And this nominal is not a non-recursive rule. It's a recursive rule because this is a noun phrase too. All the morning flights from Denver to Tampa leaving before 10. It's a noun phrase. Okay, and it should be explainable by such rules. Okay, so how is that going to happen? It's going to happen using this recursive rule. Okay, here it is. All the morning flights from Denver to Tampa leaving before 10. They didn't expand this propositional phrase or this verb phrase, ing verb phrase. Okay, noun phrase rule, determiner noun phrase, determiner nominal, nominal ing VP, nominal PP, nominal noun, and it goes that way. So how many MP rules? 1, 2, 2 MP rules, right? And how many nominal rules? 1 nominal, 2 nominal, this is the same, and 3 nominal rules. Or maybe this one too, right? 4 nominal rules. I'm not saying that 4 is all the nominal rules, but 4 nominal rules. So using this one, it looks like I can make this tree as deep as I want, right? In English, I mean, this is an ordinary, everyday noun phrase. All the morning flights from Denver to Tampa leaving before 10 is cancelled or are cancelled, right? I can say that, and it doesn't sound weird. It sounds a little bit long, but it doesn't sound weird. In English, they use it this way. Okay, so lots of recursive stuff. 1, 2, 3, 4 recursive calls of the same nominal thing. Okay, MP is really about flights. By the way, this is about flights, and this is our head. Very special part of this rule. Okay, it's called head. Every NP is going to have a head, and this head of this NP is flight. And this one, okay, there is a head. I think this VP head is leave. Okay, this PP head is Tampa. PP head is Denver. But this head of this nominal is flight. Head of this nominal is flight. Flight, flight, and flight. Okay, so the heads are important, but we are going to talk about them later. Okay, NP is really about flights. We could have said all the morning flights from Denver to Tampa leaving before 10 is cancelled. Instead, we can say flights are cancelled, right? I can replace the whole thing with a single word, flights. Okay, so that's why I understand that it is about flights. Again, we are going to talk about head thing in a few minutes, maybe. Okay, so inside this noun phrases, we have the determiners. Okay, this, a, and etc. Or simple possessives, John's car, or complex recursive versions of that. John's sister's husband's son's car. Looks weird, kind of. We don't say that kind of stuff. John's sister's husband's son's car. No, we don't say that, right? Maybe at most John's sister's car, but using this kind of, how am I going to say that? Usually I use 2 sentences. Okay, usually I use 2 sentences because these become more and more unreadable if you continue doing that. Okay, nominals are contains the head and any pre and post modifiers of it. Nominal can have a pre modifier or post modifier. Car, okay, nominal, but 3 cars or large cars, 3 large cars, etc. And we don't say large 3 cars, Another complication of English. You don't say large three cars. Do we say in Turkish in üç büyük araba, büyük üç araba? We say both of, is that, which one is correct? Üç büyük araba, büyük üç araba. Well, the both of them are correct, but their meanings are different, right? Üç büyük araba, you stress the büyük in there, right? But büyük üç araba, we stress the üç in the, I don't know, I mean,
Yeah.
something like that. Again, I mean, word order is something different. It is not part of the grammar, it's part of the semantics in Turkish. Okay, but large three cars, no, we don't say it in. How do you translate üç büyük araba to English? Three large cars. How about büyük üç araba? Large
cars, three of them.
three of large cars. Large cars which are I don't know. I think we need to use them in a sentence, right? Without using them in a sentence. Büyük üç araba yukarıda. Üç büyük araba. Büyük üç araba. When you say büyük üç araba, it's like there is a determiner thing going on. Büyük üç araba, büyük üç arabayı cümlede kullan. Niye öyle bakıyorsunuz ya? Türkçe konuşuyorum burada. Cümlede kullanın büyük üç arabayı.
Oradaki büyük üç araba.
Cümle değil ki o. Bir şey yüklem olması lazım. Yüklem söyle bana.
Yoldan küçük araba geçti.
Üç büyük araba geçti dedin ama sen. Yoldan büyük üç arabayı kullanın.
Bizi almak için büyük 3 araba geldi.
Ne? Bizi almak için
Bizi almak için büyük 3 araba geldi. Burada
üç büyük araba geldi ama.
3'ü vurgularsak
Büyük üç araba, hayır, büyük üç araba farklı bir şey. Büyük üç araba geçti. Değil mi? Büyük üç araba sanki bir determiner gibi, sanki böyle spesifik başına the large three cars. The large whatever, okay? So it is different. Okay? So I can say three large cars, those are the pre-modifiers. After the nominals I have post modifiers, right? Relative, okay. Flights from Seattle, flights arriving before noon, the restaurant that serve breakfast, relative clauses, etc. So these are the prepositions, ing word phrases, relative clauses. These are the post modifiers. These are the pre-modifiers. And each of them has their own rules. Agreement. Okay, let's talk about it. We don't say this flights or those flight. We say these flights or this flight, right? But this one doesn't care about that one. So it's just a sentence, a noun phrase in there and verb phrase in there. We don't care about the agreement in this, which is not correct. We should enforce rules about the agreement, subject word agreement. So how are we going to do that? We can do this kind of optimizations like subcategorization, like this one. As but singular as, okay? Singular as can be composed of singular noun phrase and singular verb phrase. As but plural as. It can be plural NP and plural VP, right? So I am multiplying the number of rows by 2. Okay? Plural noun phrase, plural determiner, plural nominal, singulars and etc. So I mean, if I can solve this problem for singular cases only, I can do it with the plural ones. So the extension is trivial. That's why I'm going to ignore this problem of agreement between the subject and the verb and etc. I assume that problem is kind of easy to solve. Well, which is not that easy, but okay. Easy to solve. So agreement. Okay. So this rule overgenerates. This rule say both. This rule can produce this flight, those flights, this flights and those flight. It originates. Why originates? Because it generates some of the phrases that is not acceptable by English. Overgeneration is bad. But I kind of told you how we can address that problem. Verb phrases, okay, from nouns to verb phrases now. Okay, a singular verb or a verb that takes parameters, okay, arguments. One argument, two arguments, or one argument. And these PPs, it could be a recursive, it can have a recursive structure, okay, or NP can have a recursive structure. Again, how do I know that my verb is applicable to one of these? Some of the words, for example, you don't say I read. You say I read the book, I read the newspaper. Okay? You don't use read with this PP. Okay? Or can I use it? I read books on Thursday. So I don't say I read on Thursdays, right? You have to read something. You don't say I read. You have to read something. So read is not applicable with this rule. So I have to do the subcategorization of the verbs and the nouns and the rules. Okay, that's called the subcategorization. But again, I am going to ignore all of these details. Okay, so find a flight from. Okay, find can be applied with this one. Please find noun phrase. Give could be noun phrase, noun phrase. Help could be noun phrase, propositional. And okay, you got the idea. Okay. I am going to, as I said, ignore this problem of overgenerating or agreement or the subcategorization. And we can solve this in an ugly way that will make our grammar. Remember what I said? 600 pages of English grammar. This is what it makes long. You have to handle these kind of cases. Agreements and subcategorization and that kind of stuff. But I'm going to ignore all of that problem. Okay. It is ugly. So we hide ugly stuff. We try to work on simple, meaningful stuff. Okay, so the context-free grammars, it looks like they are powerful enough for us to explain, to express our language, especially English kind of languages, using them because they are very word order dependent. Okay, but even for those kind of languages, many problems cannot be elegantly expressed, like the agreement and the subcategorization. If I can ignore them, and if we leave this ugly stuff to the computers, and if we deal the core part of the language, maybe we can get to some point with the context-free grammars. I don't think that I will be able to finish up with this chapter. Maybe I should stop at this point and we will continue next week, and we will talk about how to parse a language using a context-free grammar. Any questions? Where is Reyhan? Geldi mi yoklama oraya? Tamam, güzel. Niye gülüyorsun? Ben güldüğüm için gülüyorsun. Gülmüyorum diyor, hala gülüyor. 3, 6